introduction. My name is Andreas Fürst, and I'm the project manager of the project KW Großsulz. And first, before I will start with the presentation, I would like to thank Ms. Julia Jungwirth for her support for preparing this presentation with the content Hydro as Clean Energy, Nature Conservation and Fish-Friendly Turbines. Welcome to the Energie Steiermark. We are Austria's fourth largest energy company. We provide electricity, natural gas, district heating and energy service, and we are also a grid operator in the county in the south of Austria. And I'm working at the Energie Steiermark Green Power GmbH, which is a 100 subsidiary of the Energie Steiermark AG, and we are responsible for generating green energy. And our mission is to ensure a safe, comfortable, and sustainable life for all citizens. And we have a long experience in constructing and planning constructing hydropower plants along the River Mur. And we are always searching for new innovative solutions to improve the river systems. And hydro as clean energy with its high efficiency with about 85 to 90% is the highest of all renewable energy sources. And we know that after construction, we produce zero emissions for more than 90 years. And so hydropower is a zero carbon dioxide, zero carbon dioxide technology. And at the moment, hydropower covers more than half of Austrians' current electricity demands. And with the new European Union target of 42.5% of renewable energy by 2030, the Austrian government has set a goal of 100 renewable electricity by 2030, which we will need to increase from the current 75%. That means we have to install in total 28 terawatt hours per year. And in this 28 terawatt hours, we need for more hydro 5 terawatt hours per year. And another big argument for me is a Technical University Graz case study on a hydro plant construction showed a carbon dioxide amortization in less than half of a year. That is comparable to wind energy. We have big challenges by planning hydropower plants. On the one hand, we have to install green energy. On the other hand, there's nature conservation, and we have to avoid to split ecosystems and fish habitats, and we have to avoid negative effect on water qualities. And that's also a reason why in non-governmental organization there are mixed opinions about the efficiency of water power plants or hydropower plants. And the prospective base of the approval procedure in the future is the natural restoration law, where we have to remove barriers from about 25,000 kilometers of free-flowing rivers by 2030. That means we need more comprehensive solutions and we need appropriate locations. And this could be existing water management structures, like in the case of the KW Großsulz. What does a project like a hydropower plant means? We from Energy Styria or the Energie Steiermark ensure that we have to do a lot of ecological measures, and we have very stringent ecological monitoring before, during, and after construction. And this includes the instruction by ecological supervision during the construction period. And the result is that we improve the actual situation, like you see at the pictures beside. And before we start with a project, we have to do a lot of measures like fish drying, and we have to save plant roots, and we have to observe the fauna flora around the construction site. In bigger projects, larger projects are audited by an environmental impact assessment, which includes all the nature laws of Austria, Styria, or the guidelines from the European Union. And we have very great experts here in the green power, which can do their best to get approval in an ecological way. What should we protect? I will give you an abstract of the most deserving protection species along the River Mur, which are larger than 20 centimeters. These are brown trouts, the Danube salmon, the grayling, the brook lamprey, the barbs, and the burbots. Why why do I mention larger than 20 centimeters? Because if we would like to to protect all the fish species, we need larger diameters. This project, which is in Europe, the first project, is a little bit too small to guarantee the fish passing for species that larger than 20 centimeters. But we are working on it that, for instance, at a River Mur project like Karlsdorf, Göstorf, or Graz, we can protect also larger fish species. One of the most important criteria for us to select a turbine system is the efficiency. And the fish-friendly turbine from Nadel allows fishes to swim downstream through the turbine and has also a maximum operating efficiency of about 90 till 93%. And this is comparable to a traditional Kaplan boat turbine. They have normally 90 till 95%. And the overall efficiency, and this was a little surprise for us, is also about 80 till 85%. And this is in the comparable range for small hydro power plants. And what do we expect with this technology? We would like to reduce the head loss from the trash wreck. If it's possible to increase the grade spacing by using a Nattel fish-friendly turbine, we can increase the grade spacing to 8 centimeters. At the moment, we are discussing the grade spacing of about 2 centimeters, and you see you can increase the efficiency from 97.5 to 99.6%. That means in just a small project like KW Großsulz, we can reduce or avoid the loss of about 0.4 kilowatt for a whole year. Then in result, we can reduce the loss of about 3,500 kilowatts. And this lost energy could power an average household in Austria for a whole year. And we expect that fish-friendly turbine runners can help us to decrease the set loss. Our solution is our project Großholz. The motivation for this project was we would like to find a fish-safe turbine with a fish-safe, efficient, low-head turbine that allows fish and small deer thoroughfare with a simple structural design and within a short installation period. And we try to plan a concept like plug and play. Another advantage is that upstream stream is left untouched and restore the passability of fish species. The project Sauermann, some facts. It's a small rivulet beside the River Mur with a discharge of 1 cubic meters per second with a net head of about 2 meters. So we can produce a maximum output of 15 kilowatt with a regular working output of 120 megawatt hours per year. And you can see in the longitudinal section how easy it was to install this turbine. We just have to construct a small shaft, a trough tube through an existing dam construction of the tailwater area of Karlsdorf, and we don't need any temporary construction pit systems in the river system. So we can spare a lot of money. And in the following plan, you can see the location of the power plant, the small shaft. Here we have installed the restoration hydro turbine. We just need a control hut and the turbine cabinet. So we don't have a lot of civil works. We have a construction period of about 7 weeks for the civil works. We have about 2 months for the whole installation of the turbine, and in my opinion, it fulfill the criterion of a plug and play project. The project status: last year in autumn we installed the turbine. The operation shows us the good efficiency, and we plan fish tests in spring 2024 together with the University of Bodenkultur, Vienna, which has big expertise in protecting fish species. And so we expect that we get good results of these fish tests. Our ecological review program has started this summer, and we are also planning an installation of a fish monitoring underwater camera in spring 2024, which is the basis for the implementing of a artificial intelligent monitoring system. What are the next steps? At the moment, we have a further approval by the local authorities in Styria for another project called KB Ochsenkriesbach, which is a moor spillway flowing beside the moor. It's a little bit larger, and it's the first project where Natel cooperates with a local manufacturer in Austria. And at the moment, the Energy Styria is negotiating the price with the Austrian manufacturer. And the big hope is to work together on larger scale project, because then we have better results in efficiency. And we would like to celebrate further first turns of the runner, like you see in the picture underneath. It's like a lottery at the site, where we try to find out whether the runner is working as we have expected. So with these impressions, I thank you very much for your attention, and I wish you lots of energy. Thank you very much.
Thanks, Andreas, for that overview on the project. And now, Abe and Sterling, I want to hand over to you, and we are already curious about your insights on your technology.
Thank you very much. I will pull up the presentation. Okay, can you see it okay?
We can see it, yeah? Maybe you can go to the presentation mode.
Yes.
Perfect.
Okay, thank you very much. My name is Abe Schneider. I am co-founder and CTO at Natel Energy.
I'm Sterling Watson. I'm a staff mechanical engineer, and I focus on turbine design for fish safety.
Yeah, we would like to thank Energy Steiermark for this opportunity to collaborate in this important milestone, which is the first European installation of a fish-safe turbine of this novel design. We would like to follow up Andreas' excellent overview of the situation with a presentation that dives more into the details of the design and validation of this turbine. But first, I wanted to also make a couple of comments about the context in which we're working. Why does biodiversity matter? And the answer to this is there are at least several different ways of answering this question. One of those is philosophical, which is that living organisms have an inherent value, and it's our responsibility to minimize the damage to the ecosystems as we fulfill our own development needs. But another is more specific, and that is illustrated in the life cycles, the intertwined life cycles of fish and freshwater mussels. Freshwater mussels are filter feeders, which provide clean water simply by carrying out their lives. But mussels need fish hosts to complete their life cycle. And so by providing for safe passage of fish through hydropower turbines, we can actually encourage the successful life cycle of other organisms, including mussels, which then elevate the health of the entire river ecosystem.
Yeah, so taking a closer look at the current situation with hydropower and fish passage, conventional hydropower turbines are not safe for fish, and they can get injured in a variety of ways. But what this means is that the only way to protect fish when the turbines are dangerous is to keep them out of turbines, to exclude them. And this can be done with fine screens that are designed in a very specific way to redirect fish around a plant. But this is difficult because at most hydropower facilities, the majority of water passes through the turbines, and fish are the fish's instinct is to follow the majority of the flow. And so being able to achieve successful fish exclusion that facilitates fish passage is really difficult. Another approach that is taken in some cases is to shut down turbines during fish migration seasons. And this is, of course, undesirable for hydropower production. So we want people to really start thinking about what becomes possible when fish are included in the design of turbines. So what becomes possible when turbines are truly fish safe? So this is a look at what an ideal hydropower plant might how an ideal hydropower plant might function when its turbines are safe for fish. And what you can see here is that all or the vast majority of the flow, downstream passing flow, becomes available for fish to use to move downstream. And this also simplifies both the design and the operation of the hydropower plant because fish safety is integral to how the turbines work.
Okay, so let's take a closer look at how fish are often hurt as they pass through conventional turbines or through any turbine. Especially at low head, the most important sources of fish mortality or trauma tend to be mechanical in nature. So that's direct blade strike, where fish are struck by the leading edge of the moving runner, or blade strike in combination with mechanical grinding. So this is when fish are trapped between components that are moving and components that are stationary, or in the case of a Kaplan turbine, where there may be gaps between the blades at the hub and at the tip, these fish can get stuck in those areas and hurt. Barotrauma is also an important risk. This is the trauma related to sudden changes in pressure as fish go from the upper pool through the turbine with a sudden drop in pressure and then exit into the lower pool. But at plants like Sauerbrunn and Großholz, this is a relatively low risk compared to risks from direct mechanical injury. So one of our most important goals in our work has been to allow for fish safety at elevated speeds. And this is important because in order to have a truly scalable impact and to allow for a solution that works for as much as possible of the hydropower industry, we really need to find ways to allow for hydropower turbines that operate with conventionally high speeds to be safe for fish, not just turbines that are really slow. And so in this work, we're building upon research that has been done by others for more than a decade. On this slide, I'm sharing some high-speed, some photographs taken from high-speed video of fish struck in a laboratory in the United States at Alden Research Laboratory. And Alden was one of the first groups to quantify the dependence of the ability of fish to survive a blade strike to a ratio called the length to thickness ratio, or the L to T ratio. This is the ratio between the fish's body length and the thickness of the turbine blade leading edge. And what Alden showed quantitatively is that at high L to T ratios, so when the fish is large compared to the thickness of the blade hitting it, fish are more susceptible to be hurt at the same speeds where a thicker blade would allow for survival. And so if we look at these two strips of images, the upper strip shows fish with an L to T of about 20 to 1, 25 to 1. And if you just look at this fish being struck by the blade moving from the right to the left, the fish's body actually shows no indication of the approaching blade until suddenly it's hit, and then the fish's spine is forced to wrap around the leading edge, and this can result in spinal fracture and death. In contrast, if the fish's length to blade thickness ratio is close to 1, at the same strike speed, this fish, the body begins to adopt the leading edge shape of the blade even before contact has occurred. And when contact occurs, the radius of curvature of the leading edge is so large that it's not possible to actually fracture the spine. The fish are still at risk for a blunt force injury if the speeds are too high, but still this change in the geometry of the leading edge allows for a change in survival expectations from only 50% survival to 100% survival at this particular strike speed. So as engineers, this is really compelling and interesting, but there's a couple of issues with this, and probably the most important one from the standpoint of real relevance of fish-safe turbines to hydropower is that most hydropower turbines used today operate with strike speeds that are twice or maybe 3 times higher than this value. And so this data alone isn't enough to allow for really compelling runner designs to be manufactured. So to solve that problem, Nattel has focused on ways to allow for very fast-moving hydropower turbine runners to be also safe for fish. And really, the thing that we've added to this field is this combination of very blunt leading edges with very forward slanted leading edges. And the reason for this slant is the slant angle allows for arbitrary control over the forces that actually result in trauma to the fish. Our hypothesis is that these forces are proportional to the orthogonal component of the free stream relative velocity. And that is being illustrated in these cartoons on the lower left of the slide, where the water relative velocity approaching the turbine blade is in blue, and the effective orthogonal component of that velocity at the point of collision on the blade surface is illustrated in red. And if we can simply change the slope of the leading edge, then in theory, this red vector will shrink as a direct proportion to that angle. And if we were able to slope the angle all the way so that it was parallel to the water flow, then this force would disappear entirely. But also you would have no blade, and so you would have no turbine. And so like most engineering problems, this is a situation where we need to find a way to balance the desired benefit with the cost of implementing that benefit. And it turns out that a slant angle of about 30 degrees allows for a 50% reduction in the effective strike velocities while still resulting in a mechanical blade shape that could still be manufactured and withstand the stresses of its operation. And that results in blades that look like this. So on the right-hand side of the screen, you can see these very thick blades that are swept progressively more and more forward in a direction of rotation. And the important thing to realize is that that leading edge shape is first and foremost how the runners are designed. So they are designed to protect fish first, and then everything else about the design of the runner is derived in consequence. And so, for example, the distribution of thickness, the aerodynamic profile of the blades are all tuned given the fact that the leading edge shape needs to take a certain geometry to protect fish. So we tested this hypothesis in laboratory experiments in 2019 and published in a peer-reviewed article in 2020. Returning to the Alden Research Laboratory, we worked with Alden and with United States fish regulatory agencies to define and then carry out a test to determine if this hypothesis of slant combined with thickness could result in significant improvements in safe strike speed. And in the background here is a representation of the original Alden blade used in their studies 10 years ago. And then in the foreground is shown our new curved or slanted and blunt blade to test our hypothesis. And on the right-hand side, this chart basically depicts the strike survival on the y-axis from 0% to 100% survival, and on the x-axis is the blade leading edge slant angle. And what I've circled is the survival when the fish is struck at 90 degrees at 10 meters per second is only about 30% survival. But if we decrease the slant angle to 30 degrees at the same strike speed, almost all of the fish survive. And so this was a fantastic validation of this hypothesis. And in the course of this test, we struck almost 2,000 rainbow trout, and we were able to capture high-speed video of every single strike, which then allowed us to replicate those strikes in CFD, and then to create a calibrated computational method, a deterministic method of calculating the absolute survival of arbitrary geometries, of fish basically passing through turbines with arbitrary geometries. And this is truly the heart of our ability to create new runner shapes for new power plant applications. We are able to release digital fish particles into the flow to then track their movement through space in 3 dimensions, to post-process their dynamics and then compare that against our calibrated laboratory strike data, and then produce a computation of expected survival. And this is something that we continually are validating and verifying and tuning as we go forward. At this point in time, there are 3 different turbines in the world that use runners following this design method. 2 of these are in the United States. And excitingly, 1 is now in Europe, in Austria. And Andreas has already shared quite a bit about the development of the project at Sauerbrunn in Austria. But I just wanted to share a couple of additional points. First of all, on the left is an overview of the plan view of the site. And so you can see that the turbine takes water from a small tributary which drains into the River Mur. And one of the goals of this project was to really reduce as much as possible the civil works and the complexity of project execution. And so one of those aspects was keeping the turbine module effectively as high as possible to reduce excavation and civil works cost. And this, of course, then imposed risks on the operation of the turbine, such as could the turbine flush all of the air out of the draft tube. And so that's what I'm showing here in this bottom left animation is a simulation, an air and water simulation we performed in the process of development of the plant to ensure that air could be transported out of the draft tube and allow for full filling of the draft tube and successful operation at startup with no additional complications, which is what the plant is able to do now. On the right, we see a nice zoomed in photograph viewed from upstream and looking down the shaft of the turbine. And a couple of things I wanted to point out here. This is a 2-bladed runner. It has a leading edge thickness of just under 9 centimeters. And this is with a turbine diameter of only 62 centimeters. It is a variable speed permanent magnet generator turbine. And with the range of operating speeds, the tip speed in this machine is from around 7 meters per second to 12 meters per second. And very conservatively speaking, we expect that this turbine is completely safe for fish that are at least as large as 24 centimeters and probably much larger. We anticipate in the high 90s safety for fish even as large as 40 to 50 centimeters passing through this turbine. And we were really looking forward to the testing that is upcoming at this site. So over the next slides, we'll walk you through some of the validation work for fish passage safety that we've done on these types of turbines.
Yeah, so if you think back to the slide that Andreas shared showing a variety of fish species, 3 of those 6 were salmonids. So salmonids have been both an early and a continued focus area for us. We've conducted testing with rainbow trout, both in the field at our Monroe Hydro plant, which is 1.9 meters in diameter, as well as in our in-house test facility at small scale with a 55 centimeter diameter turbine. So what you're looking at in the video here is a rainbow trout around 40 centimeters in length passing through the Monroe Hydro plant. And we were able to conduct testing at this facility with the Pacific Northwest National Laboratory over 2 test periods. If you follow the link on this slide, it'll take you to a summary of that work. And we've additionally tested rainbow trout passage through our small scale facility at a variety of operating conditions and have observed 100% survival at tip speeds up to 19 meters per second and fish sizes up to a fish length to blade thickness ratio of a bit over 2. Another important category of fish that we have studied and have published our work on is Eulocines. So Eulocines are a really important grouping of fish, migratory fish on the east coast of North America. They include American shad, alewife, and blueback herring. And in Europe, there are also a couple of important migratory Eulocine shad species. But what was really important to study about these fish in particular is the fact that they are known to be particularly delicate, especially compared to salmonids. And so we conducted a study of juvenile alewife passage through a RHT facility in Maine on the east coast of the US 2 years ago. And we designed the study so we could collect fish from local rivers as they were migrating downstream, pass them through our turbine in groups of about 250 fish at a time, and then recapture 100% of those fish with a specially designed trap at the outlet of the draft tube. And in addition to developing the infrastructure to be able to conduct this study with minimal handling of the fish, we also installed a transparent half runner housing at the site so that we could capture high-speed video of the fish passing through the turbine. What I really like about this video is that we have quite a bit of many minutes of footage of these fish passing through the turbine. This is very much slowed down. The actual speed of this runner was 540 RPM. But you can see these fish passing through in different positions and different orientations. But in no case are the fish actually undergoing a severe strike in which they would collide with the leading edge of the blade and move with it. And so this result of observed safe passage is consistent with what we saw, which was a 100% 48-hour survival rate corrected for control mortality. And then finally, definitely want to talk about our work with eel. So eel are a particularly difficult species when it comes to hydropower because they move downstream as adults, as large adults, and they're also extremely difficult to exclude unless you have very fine screens. And so eel have been another really important focus species for us. Our testing here in the US has been done with American eel. And in 2021, we conducted a study with the Pacific Northwest National Lab at our in-house test facility here in California, where we tested a pretty extreme scenario of eel passage. So we operated this turbine at its maximum speed, which corresponded to a tip speed of 19.2 meters per second. And the size of eels that we tested with was really large compared to this very small turbine. So the turbine diameter is 55 centimeters and the size of the eels ranged from 39 to 65 centimeters in length. So in this course of this study, we captured high-speed video of 89% of the eels that were passed through the turbine. We performed assessments of both the physical, external physical state of the eel, as well as any swimming behavior immediately before they were passed through the turbine, immediately after, and after a 48-hour hold period. And we saw 100% survival over the course of the entire study. So there's a lot more observations that we collected that are summarized in our publication that came out last year which you can find at the link on this page. And I just want to note that there are some similarities between how we would expect eels to pass through turbines compared to lamprey because of their very similar body shape. And so this is just another result that we were able to get from the study that we conducted in 2021 with PNNL that's not summarized in the paper. After the study concluded, we were actually able to do a little bit of extra work because all the eels were individually pit tagged and were individually identifiable. We took the opportunity to take those eels and pass them through the turbine a second time. So this is really important because in many cases, these eels move up into the headwaters of rivers and as small juveniles, and then once they mature and are ready to move back downstream, they need to pass through multiple hydropower plants. So it's a very realistic scenario that these eels would have to pass through several hydropower plants separated by periods of days to weeks. And so we took the eels that we tested with PNNL and we passed them through the turbine a week later. And again, we saw 100% survival.
That's really exciting. But how does this all fit into the context of what's out there already? This chart shows single passage eel survival data from 60% to 100% on the y-axis and plotted against the turbine blade tip speed from 5 to 35 meters per second on the x-axis. And all of these turbines shown with icons on this plot are actual tests that have been published both for units in Europe and in the United States and in Canada. And you can see that there is a mixture of different unit types, from Kaplan's with very high tip speeds to Francis turbines with intermediate tip speeds, and then some innovative turbines like the VLH turbine and the Alden turbine with very low tip speeds. And the significance of the work that Natel has done around eel safety is easily seen on this plot. The 2021 study that Sterling just shared is, at the time, it was the highest 100% survival result for any turbine at 20 meters per second or thereabouts. But we know that in order to be able to create runner designs that are relevant to the majority of conventional hydropower applications in both existing hydropower plants that might be going through modernization or relicensing scenarios right now, as well as any new build. We know that we needed to be able to demonstrate safety at much higher speeds. And so one of the things we're really excited to share is very, very new data that we've just collected within the past 3 months, in which we have carried out a study of eel passage through a new runner, which is able to reach over 28 meters per second strike speeds or tip speeds. And we've observed over 99% survival of the eels pass through that machine. So this is super encouraging from the standpoint of being able to create relevant runner shapes that can provide a solution for otherwise conventional and high performance hydropower plants across a very wide range of tip speeds. And so lastly, I'd like to share sort of, where does all of this work fit in the hydropower landscape? So this plot in the center of this slide is a very common one in the hydropower industry. It shows a head on the y-axis measured in meters, and the flow per turbine unit on the x-axis in cubic meters per second with diagonal lines of power. And just looking at this, you can see that there were a couple of envelopes of operation for conventional propeller and Kaplan and Francis units marked, with the axial flow units being used typically at lower head and Francis units coming in at higher heads. And The green dots on this plot show the units that Natel has already built and tested so far. And as you can see, most of these units are pretty small, so under 0.5 megawatt apiece. But one of the really exciting things is that this year we've become involved in the design of much larger machines, up to 50 megawatts in size. And really the point here is that the design method of FishSafe leading edge and the rest of the runner design is very applicable across a wide range of unit size. With the small units, it's very important to allow for really thick leading edges because fish don't care if your turbine is small or big. The fish are the fish. And so in order to pass big fish through very small turbines, we need to keep the number of blades very low, and then the remaining blades need to be very thick. And that's what we see with these two-bladed machines like the one that's operating at Sauerbrunn. These machines can cost effectively achieve very high and flat efficiency curves by the use of variable speed drives, which is what is now at the Austrian RHT site. However, if we go towards larger hydropower plants, it's more common to have vertical machines that have fixed shaft speeds and large generators. And in those cases, it's not possible to cost effectively vary the generator speed. And so it's much more important to control flow and to control the pitch angle of the turbine blade to maintain high efficiency over a wide range of flows. And this is something that we're really excited to share is our work this year to develop minimum gap RHT style Kaplan turbines. And that's what I'm showing here in the bottom. For these much larger machines, for example, a between 3 and 4 meter diameter machine could produce 7 to 10 megawatts at around 10 to 12 meters of head, and do so with about 5 blades. And in this case, you can see the comparison between a conventional runner and the RHT runner for that type of application. This type of runner is able to maintain over 90% efficiency from flows as low as 40% of the design flow up to full flow, and can reach peak efficiencies between 92 and 93%. And so truly, this is an opportunity to allow for fish-safe design without compromise and in a flexible design method that can apply to a very wide range of different hydropower plants. So lastly, I think we just wanted to zoom back out and just think about, what is happening every day at hydropower plants on natural rivers. Well, organisms, including fish, but also fish, non-fish organisms are passing through hydropower plants. And it is our mission to allow for hydropower plants now and into the future to just operate every day in the simplest possible way while safely allowing all of these living things to pass through the plant. So this slide shows some results from our test in Maine in the United States, where we were intentionally testing downstream passage of juvenile Lilocines, but at the same time, we were unintentionally capturing all kinds of other fish, such as this 40 centimeter eel that was not technically supposed to have made it through the trash rack or through the 3/4 inch 19 millimeter eel exclusion screen, as well as freshwater lobsters or crawdads that all had their claws intact, 20 centimeter black bass, suckers and perch, and then also even freshwater mussels were frequently found in the live trap. And we think that it is quite possible for the future hydropower plants to just freely pass all of these organisms every day without any additional effort required. So finally, we'd really like to thank Energy Steiermark again for this wonderful opportunity, and to Next Incubator for the opportunity to share this in this session with you guys. Thank you very much.
Thanks a lot, Abe and Sterling, for this interesting insights on the technology. It was really, really detailed information. We have now the possibility, maybe as it's already a little bit late, for 1 or 2 questions. You can put it in the chat. I would have one here to Abe and to Sterling, and maybe with a quite short answer. What of challenges face in terms of upscaling? What would you say? What are the biggest ones for you?
Yes, so there are lots of engineering challenges. the design of runners is a complex one with many competing engineering constraints, from structural, manufacturing, the fish passage questions, and so on. And of course, that's what we live and breathe every day. I think the more difficult challenges actually are in management of risk in adoption. So it is, relatively low risk from a financial perspective to install a small turbine. But as we move into the world of individual units that are 10 megawatts, 20 megawatts, 50 megawatts apiece, there's quite a bit more financial risk. And that is an area that we've been working very hard to find ways to overcome those. And I think one of the most important ways is as a complete shift in our business model. Actually, when we first started working on the Sauerbrunn project with Energie Steiermark, Nat was positioned as a turbine manufacturer. And now we have actually repositioned ourselves to focus exclusively on engineering, design, and R&D of fish-safe machines, and instead to partner with existing turbine manufacturers to realize those designs. And this allows for the global scaling of these designs and the appropriate matching of existing turbine manufacturers at both the size and the physical location that is best suited to mitigate risk for power plant owners. And I think that's probably one of the most important things to share there.
Thanks a lot. So as I think there will be for sure will be some questions after the presentation, please reach out to Abe and Sterling, to Natel Energy. Please also reach out to Andreas Fürst, Energie Steiermark, and also to us, Next Incubator, if have you any question to the topic, but also to others. Please also check the websites of Natel, of Energie Steiermark, and Next Incubator, and of course also our social media channels. And for that, I really want to thank Andreas Fürst of Energie Steiermark, Abe Schneider, and Sterling Watson from Natel Energy. It was great to have you here. It was really, really interesting. And I wish you all the best and have a nice evening and a nice day. Thanks a lot. And here and see you soon. Thank you. Goodbye.
Thank you very much. Bye.